of all the applications of derivatives, one of the most important ones would be the first derivative test, or derivative tests in general, because we have a first derivative test and a second derivative test. So, what is the purpose? The objective or goal of a first derivative test is to determine where a differentiable function is increasing, decreasing, or constant. So I'm making a very strong argument here when I say differentiable function, because a differentiable function is definitely continuous. So a first derivative test is used to determine if a function is increasing, decreasing, or constant. The key here is to realize if the derivative, the first derivative, is positive on an interval, then the function is increasing. We'll have a short term or short notation, shorthand notation as an upward arrow. If the first derivative is negative on an interval, then the function is decreasing. If the first derivative is 0 on an interval, then the function is constant on that interval. So, how do we perform the test? The first step is to find the derivative. Set the derivative equal to 0. And solve for x. And that is going to give us the critical value. Now, the function, or the derivative, is 0, or it does not exist at the critical value. Using one of the previous theorems, Fermat theorem and Rolle's theorem, we saw that if the derivative is 0 at a point, then that particular point indicates that the tangent line at that point is horizontal. In other words, the slope of that tangent line is 0. So once we find a critical value, pick test points on either side of the critical value. And plug it in the derivative. The most common mistake I've seen people make is instead of plugging it in the derivative, students tend to plug it in the original function. You shouldn't plug it in the original function. You have to plug it in the derivative. And depending on the sign, of the derivative, when the critical value or values are plugged in, the function can be determined as increasing, decreasing, or constant. And that is the first derivative test. The second derivative test naturally would use the second derivative. So what does it tell us? The objective of the second derivative test it helps us identify intervals where the function is concave up or concave down. We can use shorthand notation, concave down, concave up. So, or neither. If you don't know what concave up, concave down are, consider the parabola that's open upward. That is concave up. Consider a parabola that is open downward, and that would be concave down. So the point where the function changes concavity that is from concave up to concave down or concave down to concave up is called the point of inflection. Or inflection point. So how do we go about the second derivative test? So of course the function has to be differentiable. So consider a differentiable function. F of x. The first step is to find f double prime of x, which is simply the second derivative of the function. So the next step is set the second derivative equal to 0 and solve for x. The solutions are the points of inflection. Then you plug in test points, which are x values, on either side of the points of inflection. To determine in the second derivative. So you have to plug it in the second derivative to determine concavity. If the second derivative is positive for a point, then it is concave up. If it is negative for a point, then it is concave down. And if it is 0, then it is neither. So here we have a function. It is a cubic polynomial, and we have to determine if the function is increasing or decreasing. We have to find the local maximum and minimum values. We have to find the intervals of concavity and the inflection points. So obviously we need the first derivative and the second derivative, and we could find the local minimum and maximum because the points where the first derivative is equal to 0 would correspond to local maxima or minima, because those are the critical values. The extrema always occur at critical values. So the first step is to find the first derivative, f prime of x. So 3x squared minus 6x minus 9. Set that equal to 0 and solve for x. This is going to give us critical values. So 3x squared minus 6x minus 9 equals 0. Divide by 3 on both sides. We have x squared minus 2x minus 3 equals 0. Now, we could either use the quadratic formula or factoring to find the solution to that equation. In this problem, we could actually use factoring. So if I factor, I can factor this as x minus 3 multiplied by x plus 1. So x minus 3 is equal to 0, or x plus 1 is equal to 0. So we get x is 3 or x is minus 1. So the critical values are x is equal to minus 1 and x is equal to plus 3. If we find the critical values, then naturally we can find the local maximum and the minimum. So here is the first derivative test. Minus 1, 3. We have to pick an easy number less than minus 1. Let's pick negative 2. So f prime of negative 2, we have to plug it in the derivative, is 3 times minus 2 squared minus 6 times minus 2 minus 9, 12 plus 12 minus 9, which is 15. And 15 is a positive number, and the test point that I picked is minus 2. And the derivative is positive, so the function is increasing. Pick an easy number between negative 1 and 3. I'm going to pick 0. 3 times 0 squared minus 6 times 0 minus 9. I end up getting negative 9. It's a negative number, so the function has to be decreasing over here because the test point gives us a negative first derivative. And pick an easy number greater than 3. Let me pick 4. (48) minus 24 minus 9, which is 15. Since it is positive, it is increasing on that side because the test point is 4. So where is the function increasing? The function is increasing on that interval and on that interval. So negative infinity all the way up to negative 1. You cannot put closed brackets because we cannot take the derivative at an endpoint. So which is why I put open brackets. Union 4 all the way up to infinity. The function is decreasing for x in negative 1 to 3. So that would be over here. That is the decreasing interval. So f prime is positive. F prime is negative. And back again, f prime is positive. So clearly, if a function goes up, then it comes down, then that particular point has to correspond to a local maximum. And since the function is going down, then up, whatever value that I see here has to be the local minimum. So what are the local minimums and local maximums? So at x is equal to negative 1, we have a local maximum. So f of negative 1 would equal Now we have to plug it in the original function. Negative 1 cubed, negative 3 times negative 1 squared, negative 9 times negative 1 plus 4, I get 11. So the local maximum is the point minus 1 comma 11. We go for the next critical number. At x is equal to 3, we have a local minimum. So f of 3 is 3 cubed minus 3 times 3 squared minus 9 times 3 plus 4. 27 minus 27 minus 27 plus 4, I get negative 23. So the local minimum is at positive 3, comma minus 23. So that's the first derivative test. Now what is the second derivative test? That is going to give us the concavity. So obviously we've got to find the second derivative first. The second derivative is six x minus 6. Set the second derivative equal to 0, and we solve for x. So 6x minus 6 equals 0, which would mean 6x is equal to 6, which implies x is 1. So the inflection point is x is equal to 1. Pick an easy point less than 1 and plug it in the second derivative. So f double prime of 0 is 6 times 0 minus 6. I get minus 6. F double prime of 2, easy number. So 0 is the test point here. 2 is the test point there. We get 6 times 2 minus 6, I get positive 6. So f double prime is negative, which would imply the function is concave down there. F double prime is positive, which means the function is concave up there. So the function is concave up or concave down for x in minus infinity to 1. The function is Again, we put open intervals because we can't include the endpoints. And that is the second derivative test.